Good morning, ladies and gentlemen. Let's actually start off. We need to build some skills. And so before things get too complicated with our compound circuits, we're going to work on analyzing a circuit fragment, which is what these are.
Yep.
No battery involved, just sort of applying our skills to analyze this segment right here, this fragment right here, okay? So in this picture, we were missing two things here. We're missing this too.
Yeah.
So we have, is this a parallel or series?
Well, it looks like it's one after another, so that's got to be series.
Yeah, so we're talking about in series, and so we have, a certain set of rules that we follow for series
Yeah.
circuits.
What do you know about a series circuit? If you got 5 amps coming in,
Well, that means that the current is going to be the same throughout the whole thing,
that's
right?
That's right.
Okay, so for a series circuit, the current is the same throughout, but the voltage is going to be different.
Right.
Right.
Depending on the resistance.
Yeah, depending on the resistance here. So let's go ahead and just start with this first one.
Well, first of all, what is that law that rules all of electrical currents?
Ohm's rule, right?
Yeah.
Or Ohm's law?
Yeah, Ohm's law.
Ohm's law. Okay, so V equals I times R, and we're trying to find the voltage here, so we can just multiply, right? 5 amps times 2 ohms gives me 10 volts.
So that's 10 volts is the potential drop across that 2 ohm resistor.
Okay. And then as we approach this one, I want us to know the resistance here. We know the voltage here. Could I solve this for resistance?
Yes, ma'am.
I sure can. Now our voltage is 6 volts. And what do we know about the current? We said it's the same
It's 5 amps.
everywhere. And is this 1.2?
It is 1.2. It's 6/5.
1.2 ohms. Okay. All right. So so what do we do here? We recognize that one, it's a series circuit, and then we have to realize that when we're in series circuit, our current is constant. It's the same.
Everywhere.
It's the same everywhere, and we can use Ohm's law to kind of dissect it.
Yes, ma'am. That's a great start.
Okay. All right. Let's go ahead and move on to this guy right here. So
This looks different. What is this?
This is the parallel circuit, right?
Yeah. There's
and
more than one path for current to follow.
yeah, I can go this way or this way.
Yeah.
And what do we know is the same in a parallel circuit?
Well, the potential difference.
Yeah, they both have equal access to the battery, right? So this resistor has equal access and this one has equal access. So what does that mean for the voltage up here? It's going to also be 6 volts,
Yeah.
right? Okay, so now
What is that?
next?
We got the 5 amps coming in from the left. What happens to that current when it hits that junction?
Well, one right here?
Yeah, that junction right
So it's
there.
going to split,
Yep.
right? Now we have 3 amps going this way, and then the rest of them are going this way, right?
So how much would that be?
So it's got to be 2
2
amps,
amperes.
right? And if we think about, for our parallel circuit, we know that the total current in parallel is going to be equal to the first one plus the second one.
That's right.
Right, and however many more we have over here.
Yeah.
Okay. So.
Could we find the resistance here?
Oh yeah. Did I forget to draw one right here? Oh yeah, we're trying to find the resistance here as well, and right here. I knew I was forgetting something. Okay.
Well, now that we've got the voltage and the current, it's going to be easy, isn't it?
Yeah. So we're just gonna go ahead. Resistance equals the voltage over the current, right? And our voltage is 6 volts right here, and then our current through this part right here is 3 amps.
6 divided by 3 be 2.
2 ohms. So this is a 2 ohm resistor. Now, can I say that this is 2 ohms too?
Nope, because it's not.
No, it's not, right? We've got a different current right here.
And you got a different, yeah.
Oh, not, sorry, wrong one.
You got the same potential difference, but a different current.
Yeah, so the voltage is 6, right? But our current here is
6 divided by 2 is?
3. Okay, so 3 ohms here.
Sweet.
Okay.
So, see how simple this is, boys and girls? And if you understand what's going on with a series and a parallel circuit, and you can just look at fragments and understand that you can break them down. If information's missing, take what you know.
And if you are like, Miss Moore, I'm completely lost, think about this chart we made the other day. What's the same? What's different?
What happens to the resistance?
Yeah.
As you add more resistance, yeah.
So we said that in series, what is the same? Well, our current's the same, and our voltage is changing, right?
Yeah.
Okay, our potential difference there. And then parallel, our voltage is actually the same, right?
Yeah.
6 and 6 because they both have equal access to the battery.
Yeah.
And what's different every time? Well, our current, we have to add those up like such,
Yeah.
okay? Now in series, if you have more resistance, if you add more resistors, then what happens to that resistance? It's going to
Mo.
increase. In parallel, if we were to add another resistor in here, it's like opening up more doors in our cafeteria, our area is getting bigger, it's going to decrease the resistance.
That's right.
And so you should be able to do this.
Yep.
Okay. All right. So, okay. So this slide says to analyze circuits, start by making a diagram that includes all information. So go ahead and take out your what's this one called?
That's the if you connect two bulbs in series, a 60 watt, which will burn brighter.
Oh, yeah, it's from the last lesson. It's the 60 watts to 100 watts worksheet.
Yeah.
Plus lesson.
We're going to be analyzing circuits, and the first step you got to know what to do is you take the information. Sometimes it's words, sometimes you're given a diagram, but you have to make your own that includes all the information.
All right, so what do we have here? So it says draw a diagram with both bulbs in series. So we'll do in series with a 120 volt source. Okay, so here we are.
120 volt source. And one bulb is 240 ohms.
240. Okay, this is 120 volts. And then this up here is 240 ohms.
And the other one's 145.
Okay. All right, sweet.
That's all the information you're given, and that's the way you should start.
Okay, so should we do anything with this?
No, we got to
Okay.
take it.
All right, let's rock and roll. So, reduce all elements to one equivalent resistance.
Yeah, that 2 should be
I
gone.
was like, wait.
Typo.
So what does that mean over here? Like, how does that look?
Well, the battery doesn't know where the wires go.
No.
And from the battery standpoint, what one resistance could replace all the elements?
Well, so this is in series, right?
Yep.
And so for our resistance, we have to add them up, right? So like this one plus that one.
Yeah.
So basically, we'll make it look like that. So we'll do 240 plus 145.
Let's see, that's going to be 385.
385, yeah. So 385 here. 385 ohms.
385 ohms and 120 volts.
Yes. 120 volts. Okay, so
Sweet.
that's
a first step.
That's a really important step.
Yep. Can't do anything until you do that.
Okay. Right. So find the total current pushed by the battery through the resistance.
So now we can do that now that we have the equivalent resistance.
Now, can I put it here, over here?
It doesn't matter.
Right. Okay.
As long as it's in the flow, the ammeter is right.
Okay. So now, if I want to find the total current, how do I do this?
Ohm's law rules the
Ohm's law.
electrical universe.
Right. So we've got this equals volts over resistance. So voltage is 120 volts. Resistance is 385 ohms. And Miss Moore. And
I
Miss
can't
Boyd
do that
can
in my
cut
head.
their head. Okay. So 120 divided by 385, and I get 0.3. We'll call it 0.31.
0.31 amperes.
0.31 amperes. 0.31 amps. Okay.
Okay, so we got 0.31 amps flowing through the equivalent resistance, but it's also 0.31 in our original circuit.
Yeah, over here. So if I was to put it here or
Yeah,
here,
go ahead
or
and
here.
put that ammeter in
Yeah,
over there.
I could put it right here.
Yeah.
Right? I could put it right here.
Anywhere you
right there.
want,
I can
as
put it
long as
anywhere.
it's in the flow. It'll
Yeah,
be the
and
same.
so we got
0.31
0.31
amps.
amps right there. Okay. Okay, work backwards to find the voltage across an element and the power.
So let's choose, which one do you want to choose? 240 or the 145 ohm?
Let's just do 240.
All right, so
Okay. So we're
first,
finding the
what's the
voltage?
voltage going to be?
Okay, so we put a little voltmeter right here. What's it gonna be? Well, we know that V equals I times R, and our current is 0.31, right?
Yeah.
Because the current's the same throughout the whole thing, right?
Yeah.
And then our resistance through this one right here is 240 ohms. Okay, so 0.31 times 240. And I get 74.4.
Let's call it 75.
I think it's a good idea. 75?
75 volts. Now, challenge, boys and girls, without using Ohm's law, what's going to be the voltage drop across a 145 ohm resistor? You can't use V equals IR. Use your knowledge of series circuits. If it's 75 volts across the 240, what's it going to be across the 145?
Here's my hint.
Yeah.
The ups equal the downs.
Oh.
All right.
So the two voltages across the bulbs has to equal 120.
Yeah, so Miss Moore is going to use the calculator. 120 minus 75, it should be 45.
So 45 volts.
Now, if you guys want to go and check my work there, please feel free
Yeah,
to
go
do
ahead
so.
and put that 45 volts in a circle.
Oh, snappers, yeah.
And that's
we'll go like that.
There you go.
Yep.
Are you guys starting to see what's going on here? What the procedure is?
Yeah, and so what we did so far, Mr. Boykin, is we wrote down everything, right? And then we reduced the battery doesn't know what it's looking at.
That's right.
And we reduced it down to the simplest
Single equivalent resistance.
a single equivalent resistance. That's what I need, okay? And then we say, hey, what is the current running through there? We pop our ammeter in there.
Yep, that's important.
We do our thing, and then we had to work backward to find the voltage across each thing. And why can we do that? Well, the current is the same in both of these because that's in a series circuit. The current is the same throughout.
Yep.
Okay. This is making sense. Okay. Parallel circuit. Okay, parallel circuits have more than one path for current to follow.
Yep, we saw that earlier, and this is review.
Yeah. So
I do believe it's
I'm sorry. Actually, go back real quick. We said and the power here.
Oh, we didn't do the
We're
power.
gonna do the power.
Let's see, power is intravenous, isn't it?
Yeah. So PIV is that?
Yeah.
Where do I put the power at? Should I just write it right here?
Yeah, I do the calculation somewhere and then write the result under the bulb.
Power is intravenous. Okay, so our current is 0.31 amps. Can you see that, Mr. Boykin?
I can see it, yeah.
Okay, and then our voltage here was 75 volts, right? 0.31 times 75. 0.31 times 75, and I get, we'll call it 23 watts. So 23 watts right there. Okay, and then we'll do 0.31 times 45, right?
Yeah.
Okay, and I get, we'll call it 14 watts.
Okay, now I'm going to stop right here and let's take a look at this. Remember, we started off with a power rating of the bulb when it was in the circuit by itself. And if you give it 120 volts, it'll give you 60 watts. If you give it 120 volts, this will give you 100 watts. Okay, however, when you put them in series, remember that's Weird Lab, all bets are off. Because the 60 watt bulb that has 60 watts stamped on the top of it does not have access to 120 volts. It has to share with the 100. See, it's only got 75 volts. So its power output is going to be less in a series circuit. And the one that was brighter, the 100 watt bulb, is now puts out less because it has less resistance.
So this one puts out more, right, Boykin, than
Yep.
this one in terms of the power and therefore how bright it is.
That which was 60 watts is now putting out 25, and that which was 100 watts is now putting out 14. Why is that? Well, because it's in a series circuit, it's not getting all the voltage at once.
I know.
It has to share. I want all the M&Ms.
Okay, so we're good there. We've covered all of our bases. Okay, so parallel circuits have more than one path to follow. One path for current to follow. More paths, more current.
That's right.
Were we going to do one for that, or were we just going to
Let's see. We got 15 minutes here on this.
Let's just keep going.
Let's just keep
Okay,
going. This is just review.
Okay, the potential across the elements is the same for both sides have access to the battery. We know this, right?
Yep.
Okay. The current through any branch is determined by the resistance there.
Yep.
Yeah. Okay. For a parallel circuit, the equivalent resistance for a parallel circuit is 1 over.
It's an inverse relationship.
This equation, yeah.
The more resistors you add, the less the total resistance is. It's an inverse relationship. That's why you got this. And all these are is buttons on your calculator, that x to the negative 1.
Yeah, and if you're like, Miss Moore, why? Do you guys remember that that scary video that Mr. Boykin showed you with the eerie music? And they added the two resistors together, and it made this one resistor with a bigger area.
Larger cross-sectional area that
Yeah.
allows more current to flow.
Yeah, more current to flow. Okay. The total current through the source is split between the paths, right? And so for a parallel circuit, when we're adding up the current, it's the first one plus the second current plus the third current. And we saw that with our first fragment.
Yeah.
Okay, it was our second fragment over
Yeah.
here. Okay, finally a practice problem. Here we go. So 3 resistors, a 60 ohm, a 30 ohm, and a 20 ohm, are connected in parallel across a 90-volt battery. So what's the first thing we need to do?
We need to make a diagram that includes all the information. So boys and girls, we're going to do one. Let's see if you can get a parallel circuit started
Go ahead and start.
with these 60, 30, 20 ohm resistors and a 90-volt battery. Oh, that blue doesn't erase, does
Blue
it?
is aggressively, it just doesn't want to go. Don't erase me. I'm too good to you. Okay. How much volt? 90 volt. Boop, boop. Okay, and then 3 are in parallel.
60, 30, 20. So just go ahead and...
Is that enough room?
That's plenty.
Okay, so 90 volts, right?
90 volts. 60, 30, 20.
60, 30, and 20.
Now, quick question, boys and girls. The current is not going to be the same through each resistor. Which will resistor have the most current? Which resistor should have the most current going through it?
Okay, well, the most current means the least resistance, right?
Uh-huh.
So this one will have the most
So
current,
we should
right?
have the most, then the least would be the 60 ohm.
Okay, so what's the next thing we want to do here?
Well, is there a...
Is there a next slide thing?
Well, we need to reduce it to one equivalent. Let's go back through our
yeah.
the
Oh
thing
yeah,
that
we don't.
we did.
Yeah, we don't have any other slides here helping us. Okay, so probably should have moved this over a little bit.
From the battery
Okay.
standpoint,
From the battery standpoint, what does it see?
you can do the calculations over on the left and all that.
Yeah, there we go. There we go. I was like, oh. Okay, so we need to figure out what this equivalent resistance is going to be. How the heck do we do that? Okay, so 1 over 20 ohms plus 1 over 30 ohms plus 1 over 60 ohms. Okay, that's. Do you, Mr. Boykin, when you do this, do you say the resistance parallel equals, or do you say like how do you?
Well, what I would do is I'd put the answer 1 over.
1 over.
Yeah,
Okay.
but
Okay.
now, here's the thing. One way you can tell you've done it right is your answer should be less than any of the ones you've got there.
Yeah, because it's less resistance here.
Yeah.
Okay, so 20 to the negative 1 plus 30 to the negative 1 plus 60 to the negative 1. Yikes. And I get 0.1. Are we done yet?
That is not the answer.
No, just gonna take that to the negative 1 and we get 10.
10. So the equivalent resistance of all these,
Is
10 ohms.
okay, so we'll put that up right here. 10 ohms.
Okay, now what's the next step that we did, boys and girls? We've got the equivalent resistance. Now what did we have to do with this equivalent resistance?
Okay, so we want to figure out what right here,
Over
right?
here, yeah.
Okay, what the total current
We
is.
need to find the current.
Okay.
V equals IR.
Yeah, so
I is equal to V over R.
V over R. So voltage is 90. Our resistance is 10 ohms.
It's going to be 9 amperes.
That's going to be nice and easy. Okay, so 9 amps here for the total shebang.
Yeah.
Okay.
All right, now what's the same everywhere in a parallel circuit?
Our voltage is going to be the same.
So
Right.
each one of these resistors has 90 volts across it, because you can see each one has access to the battery.
Yeah, yeah.
And but what's different?
The current.
And so which one do you want to do first?
Let's just do this one first
So-
here.
You got all. Oh well, put an ammeter
Right
in.
there?
You're doing the right thing, yeah.
Yeah. What were you gonna say?
Well, I was going to say all the room on the right of the resistor.
Yeah, there's so much room. You'll squeeze it in
I know.
here. Okay.
Yes.
Okay. So how do I figure out this current? Right.
V equals IR. I is equal to. Oh, we did it a minute ago.
Over
V
here.
over R.
So the voltage, which is 90.
90 volts divided by 60, 9/6.
Is that 30?
That's
No, 1/3.
9 divided by
Wait.
6 is 1.5, isn't it?
1.5. Okay, so we get 1.5 amps here. Now, well, I'll keep going here. So, put it over here this time. Doesn't matter. Okay, so what's our voltage? 90 volts. What is our resistance here? It's, 30 volts. Mr. Boykin, is that 3?
I think it's going to be 3.
That's 3, right? Now, without doing any math, could you figure out what this one is? I mean, you have to do a little bit of math.
Well, well, the current leaves the battery,
Mm-hmm.
and it gets to the first spot, and it splits, and 1.5 goes there through then, and then the rest of it goes up to the next junction,
Mm-hmm.
and 3 amps goes through there. How much is left?
Well, our total current is 9, right?
Yeah,
So minus 3, which is 6, minus 1.5, which is
4.5.
4.5. So this should be 4.5. Okay, so let's do some math. So 90 volts divided by 20 ohms. 9 divided by 20. That should be what we said.
4.5.
4.5.
Boom, boom,
right?
boom, boom.
Okay, 4.5 amps. Okay, so yeah.
And
That's
you know, we could calculate the power, but we're not going to.
Yeah, you could if
But
you're
we
dying
could
to.
ask you to do that.
Yeah, you know, what if I want to know which one was going to be the brightest, right?
Yeah.
Calculate the power.
Yeah.
Okay. And the one with the highest number would be.
So here's some review,
Brightest.
boys and girls.
If your house is your house wired in series or parallel?
And what difference would it
What
make?
difference would it make? You should be able to answer this question.
Yeah.
Okay. So now you know what I'm gonna. I have 3 slides here. I'm just gonna assign them for homework.
All right.
Okay. So what is the same everywhere in a series circuit and a parallel circuit? What changes from element to element? So what's changing, what's different in a series and parallel circuit? And then lastly, what happens to the resistance as you add more elements, more resistors, whatever it is?
Yeah.
Lights, bulbs, whatever.
Yeah.
In a series, in a parallel circuit.
So, and I probably should have put in equivalent. What happens to the equivalent resistance
Oh,
as
yeah.
you add more? But that's my bad. So,
That's good. Okay.
and I think that's
so,
it.
So yes, so that is the main homework. But in addition to that, we are gonna have you guys do on page 574,
Page 574,
numbers 41 and 42,
41 and 42,
and then 50 and 52.
and 50
Mm-hmm.
and 52.
All right, that's all we got.
Boom.